Okay, question 82. List the following alcohols in order of decreasing acidity. So the way that the acidity data is given to you is in terms of Ka. So if something is given to you in Ka, it's totally possible to compare acidity, but in terms of organic, it's just best to go ahead and get out of that mindset and start thinking about acidity in terms of pKa. So I'm going to go ahead and do the Ka to pKa conversion for the first molecule. And then after that, hopefully take a second, pause the video, make sure that you're comfortable doing these calculations, and then we'll start it back up. So I'll go ahead and do my calculation first. So that's the Ka value, and converting to Ka to pKa is very, very simple. All you do is take the negative log, so take the log of that, and then we're going to just take the negative. So negative log of the Ka is the pKa, and that turns out to be about 12.24. So 12.24. I'm just going to abbreviate it as 12.2. So at this point, I'm not going to show the other calculations. I'm just going to go ahead and do them, and then we'll start back up again. Okay, so after you do the calculation, these are the resulting pKa's. So a trend that you might notice is, again, if we wanted to rank these guys in terms of decreasing or increasing acidity, let's say 1 is going to be the most acidic, and let's say 3 is the least acidic. So of these, the most acidic is going to be the compound with the lowest pKa, and that's going to end up being the compound that has the 3 chlorine atoms attached. So this guy is going to be the most acidic, number 1. Then the second most acidic compound is going to be 12.3 versus 12.9, so it's 12.3, and that's the alcohol that has 2 chlorine atoms on it. So what you'll probably notice is that as we tack on more electronegative atoms, you're going to start again withdrawing electronegative or electron density because of the electronegative halogens, and because of that we're going to be stabilizing that resultant negative charge on the oxygen once you actually remove a proton. So for that reason, 2 is going to be slightly less better at removing electron density from the oxygen versus this first compound over here, and so it's going to be a little bit less acidic. So same thing for the final compound, this guy in the middle. This guy is going to be the least acidic because this compound, this alcohol, only has 1 halogen attached. You only have 1 electron withdrawing group, and so this singular chlorine is going to be the least suited or the least able to remove electron density from this oxygen once you actually break that oxygen-hydrogen bond and put a negative charge. And so that negative charge is, one way to think about it is that negative charge is going to be the least happy on this oxygen right here, because you have a whole bunch of electron density on that oxygen, so you're really in the red. And then as soon as you start tacking on more and more electronegative groups, so going from 1 chlorine to 2 chlorines to 3 chlorines, you really increase the ability to withdraw that that destabilizing really hot negative charge on the oxygen. So that's why this compound is the most acidic, and then the next acidic, and then finally the least acidic over here. And that's pretty much the explanation. And I guess if I had to take it and write write down an answer, so we would say that the easiest way to explain this away is that as the electronegative groups are added, any resulting negative charge in the deprotonated oxygen is going to end up being stabilized to a higher degree. And again, this is simply via inductive effects. There is no resonance going on here whatsoever. So this is only via electron withdrawing or inductive effects from the chlorine. So that's how you would notate these inductive effects.